Toys are very important part of any children's life. Toys can also become a very important tool for research, and this need not be only research in laboratory. Toy models are extensively used even in theoretical physics and various different branches of science. The amazing part of using toys as a model system is that you can play with them. That element of play is very critical when one is trying to think about design, and also when one is trying to understand some specific abstract principle, because it gives you a visual tool. Now imagine if you can use the same thinking and extrapolate that to research. Specifically, if you can take this particular viewpoint and use it in building new materials. Materials, as you know, are a very important part of human life. They actually are part of each and everything what we do in our life. And the question is that can you use something like a Lego block and make Lego blocks of atomic materials, meaning, let's say, materials which are made of one atom thick? Can you grow such kind of materials? Can you stack them one on the other? In an essence, the new research which is emerging out in the recent years tells us that the horizon is limited only by our imagination. So, for example, the possibility to combine something like a single layer of carbon, which is usually called as graphene, with the other two-dimensional crystals has expanded this particular thinking dramatically. With so many combinations which are existing in nature, imagination is indeed a limit for this way of thinking. So the question is, how do we imagine a material built to such kind of an order? And the fascinating aspect is to stack them one on the other. Now, for example, imagine a situation where you have a high TC superconductor, and that high TC superconductor actually is placed on a room temperature, some kind of a material, let's say some kind of a semiconducting material. In this case, I'm just showing it as exotonic superfluid, which is a very exotic kind of a material which is made of two-dimensional semiconductors. And that particular platform can be put on a silicon chip. And the advantage is that you can now build Lego building blocks one on the other, such that you now have a single layer of some particular material. On top of that, you build another material, and on top of that, you build another material. Now, what is the advantage? The advantage is that there are new physical properties you actually can obtain from such kind of stacking of these materials. And this is one of the cutting edge prospects of research, because you would now be able to combine physical properties of material 1 on top of material 2 and obtain a new property which is neither present in 1 or 2. By combining them, you might actually get an exotic kind of application out of this particular thing. Now, this blueprint of stacking of so-called 2D crystals, two-dimensional crystals, like a Lego building block, is indeed a very fertile research area. So, for example, you can take a monolayer, put it on top of the other. The resulting stack is now an artificial material which is assembled in sequence. Please remember, if you put a particular material like a graphene and hexagonal boron nitride and a molybdenum selenide or molybdenum sulfide, some kind of material would actually be stacked one on the other. Depending upon how you stack them, the physical property actually can play a very critical role. Interestingly, when you take such kind of layered materials, there can be forces between these two materials. And such kind of forces usually obey van der Waal interactions, and van der Waal forces play a critical role. One of the challenges is to design these kind of van der Waal materials such that you would be able to stack one material on top of the other and make them stable in laboratory situations, and hopefully also in the realistic, harsh outside world situations. This is an enormous potential to really innovate, where the path from laboratory to industrial scale has really boomed in recent times. So the idea is you start with a manual assembly of such kind of structures. Then you scout for new physics and high quality prototypes, and those prototypes are generally prepared in the laboratory. And now you create something called as van der Waal epitaxy, which is a very important way of kind of combining such kind of materials. And you can grow such kind of stack layers in the laboratory using certain kind of methodologies and tricks. And you create roll to roll transfer on such kind of materials. These materials can become platforms for silicon chips. These can become materials for optoelectronic applications. And it all crucially depends on how you grow these materials and then isolate them and stack them one on top of the another. This has really created an enormous potential. So this is not just a throwaway idea, but there is enormous amount of research which is going on. And this dates back more than a decade, where the so-called materials of van der Waal heterostructures have been innovated. This is one of the fantastic review articles, a perspective article by Andrew Geim, who actually was the co-inventor of graphene, a Nobel laureate, and there is a fascinating amount of research which is going on. This particular article, of course, is also available on archive. I will link those articles in the description. Do have a look at it. So the whole point here is that you can now take materials and prepare those kind of materials in the laboratory. How do you prepare them? What are the prospects? These are some of the interesting questions which are addressed in this particular review article. What is crucial is that it now crucially depends on only how you stack these materials, which means that it is up to your imagination, and how you want to utilize that imagination is something totally up to an individual or also group of researchers. And this can be translatable because these kind of preparation of materials are not as intensive in infrastructure as, let's say, some very sophisticated methodologies. Of course, you can always iterate the processes and techniques and use more and more sophisticated methods for characterization and also preparation. There is an enormous potential for such kind of materials, and the industrial applications of these materials is already there. Various people are working on, photo detectors, and various techniques have been utilized. Indian research community is very active in this particular area. A lot of condensed matter physics people who work on electronic structure are also interested. There is huge amount of theoretical physics associated with this, outstanding experimental physics, device physics. So this is a great area for even students to get into and also explore. And probably a startup should actually be taking up these ideas and exploring it in deeper way. So I hope this will be useful for a lot of people who would want to use their imagination, because imagination has no limits.